So now we've accrued really quite a large collection of results about what monomorphisms look like in set to the power of c. We can finally get to one of the most interesting kinds of questions we can ask about this category set to the power of c, which is, what does the subobject classifier look like? So the subobject classifier gives us our notion of truth, allows us to think about the logic of these different kinds of categories. And it's really quite a fascinating thing because you sort of get a natural notion of truth for the sort of particular universe, which is the kind of set to the power of c which you're studying. For example, if you're studying the category of dynamical systems, then the truth value object includes sort of a notion of how much time it's going to take for something to fall into a particular dynamical system. Or if you're studying the category of graphs, the subobject classifier sort of involves a natural notion of saying whether vertices and edges are present in a particular subgraph. So we're now going to talk in general about the subobject classifier. So let me just recap the definition very quickly, and then we're going to talk about how we can actually compute these things in set to the power of c. And it's largely using the Yoneda lemma. So the subobject classifier consists of an object omega and an arrow t from the terminal object into omega. And it's such that for any monomorphism M, let's say from an object X to an object A, there exists a unique arrow chi subscript M from A to omega, which is such that we have this pullback square here. So another way we could say this is that this chi of M here, this classifying arrow of M, is a unique arrow such that M is the pullback of this true arrow T along chi of M. Now, there's various equivalent ways to say this. So this thing I've put in blue brackets here, an equivalent way to say it is that M is the inverse image of T along chi of M. Another, so if we want to write this algebraically, we could say M is equal to chi m to the minus 1 of T. That's just sort of notation for saying that M here is the inverse image of T along chi of M. And then there's a sort of arrow-centric way to say this, which is to say that for any arrow H which comes into A, we have that H is in M if and only if chi m after H sends everything to true. So it's equal to true after exclamation mark H. So think about this kind of case like this. And of course, this notation, for example, exclamation mark X, just denotes the unique arrow from X to the terminal object. Okay, so this is the thing. If we have a monomorphism, by the definition of a subobject classifier, we can find this kind of classifying arrow, chi subscript M. So we can always go from something like this to something like this. But it turns out we can go the other way around as well, because if we have an arrow into omega, we can always pull back true along that arrow to give us a subobject. Now, when you're doing a sort of pullback of a monic along an arrow, you're always going to get a monic, but you don't really know which exact monic you're going to get usually, because monics are sort of usually thought of up to equivalence. So up to equivalence of monics, you know what you're going to get, but which one of the sort of family of equivalent subobjects of A you're actually going to pick out is not specified. So for this reason, we just assume that we've got a sort of specially picked stock of sort of representative monics. So for each class of equivalent monics, we sort of pick one out. So the way that we do this, and this is really just for sort of convenience of notation. So say we have an arrow A, which goes into omega. Well, then we know if we pull back So here's the idea then. Suppose we have an arrow little a that goes into omega. Well, we know that if we pull back true along A, then we're going to get a sub-object of A. And we also know then that little a here is going to be the classifying arrow of that sub-object A star. And we also know that little a here is going to be the classifying arrow of that sub-object. And that's all well and good, but you know, there could be many sub-objects of A which we could pick here, because just saying that we get this arrow here from doing a pullback doesn't really tell us the exact form of this. It just tells us it's up to equivalence. So what we do is, for every arrow little a into omega, we assume that we've got one of these particular kind of sub-objects of A, which is the pullback of true along A, sort of ready selected. Okay, and we denote that as A star. So this is just sort of one of the equivalent monics which could be considered to be the pullback of true along A. That's what A star denotes. And in the category set to the power of C, there's a very natural choice for what A star ought to be. I mean, if we can pick any one of these load of equivalent monics, why don't we pick an inclusion monic? Okay, because then we have all these kind of nice connections with our kind of set theory thinking too. So we might as well let A star be the inclusion monic, which makes this as a kind of pullback square. So this, you know, doing this kind of thing gives us a very nice way to use the sub-object classifier, because we can basically think of it now as giving us a sort of isomorphism of arrows. Okay, because if we have an arrow little a into omega, then we can always pull back true along that arrow a, or if you like, we can take the inverse image of true along little a, and that'll give us this sub-object A star. On the other hand, if we have A star, we can always just find the classifying arrow of it, as in we can compute chi of A star, and that'll be A. So we can go backwards and forwards between these two different things. We have this kind of sub-object classifier isomorphism present, which allows us to switch between arrows from A to omega and sub-objects of capital A. And now we can use this idea to start to compute some of the structure of our sub-object classifier. So this is where it starts to get pretty interesting. So let's suppose we have an object E in our category C, and of course we're interested in working out stuff that's going on in set to the power of C. And here's the sort of fundamental correspondence which we use. So an element theta, an E-type element of omega, is going to correspond under the Yoneeda correspondence to this arrow theta under arrow, which goes from hom E comma blank to omega. But that's just an arrow from some object into omega, and so using this kind of correspondence, we can see that this arrow theta, we can see that this theta under arrow here is going to correspond to a sub-object theta under arrow star of hom E comma blank. And these horizontal lines all denote isomorphisms. So basically, the E-type elements of omega are just going to correspond to subobjects of Hom E, blank. And so if we just sort of find the set of non-equivalent subobjects of Hom E, blank, and again, we might as well represent those as inclusion monics because it's easier. And if we do that, we can essentially answer this question of what are the E-type elements of omega. In fact, since we have this correspondence and since we don't really know how to sort of label the elements of omega of E, we might as well literally consider them just as inclusion monics of Hom E, blank. So in other words, basically the elements of omega of E can really just be thought of as substructures of Hom E, blank. So let's apply this to our category of functions. So now we want to find out what are the E figures of omega to the E. Okay, so we really just ask ourselves, what are the sort of fundamentally different subobjects of Hom E, blank? And so we draw out Hom E, blank. Here it is. It's a vertex called S with a loop called identity of E. And then we just ask ourselves, what are the different kinds of subobjects? And we'll just consider the inclusion monics because that just makes things cleaner. And we see that we have three different subobjects. We have this empty subobject, which I'm calling psi E false. We have this subobject here, which is just where we only have the vertex. So I call this psi EM. And we also have this kind of full subobject here, which I call psi E true, which just has everything in it. And so we can really think of the E-type elements of omega here as this set of psi E false, psi EM, and psi E true. Okay, so that tells us about the E figures of omega. We also, and so these sort of three things here are essentially going to be the loops of this sort of bouquet that we're trying to make, which is going to be our subobject classifier in this category of functions. We also want to get at the vertices. So again, we just find Hom V, blank, which just consists of a single vertex, and ask ourselves, what are the different subobjects of Hom V, blank? And we find that there are two, just the empty one, which we can call psi V false, and the full one, which we can call psi V true. So this is the set of vertices of omega. It's just going to be this set, psi V false and psi V true. So we want to, of course, go further. We want to understand what the kind of actions are. In other words, we have these vertices and loops, and we want to understand how they're linked up, we want to understand which loops have which vertices and so on. But let's just postpone that for a moment and talk in more generality. So I'll go to the most general case now. We'll just think about what's happening in a topos. And in general, if we have a subobject little a of y, and we also have an arrow f from x to y, then we can always consider the kind of pullback of a along f. And we normally denote this as this monic f to the minus 1 of little a. And we don't really know what to call the kind of object that this monic emanates from, so why don't we call it f to the minus 1 of capital A? Okay, so we really have this kind of situation, this kind of pullback square drawn in orange and blue here. And so what we're really saying is we're going to let f to the minus 1 of a denote the kind of inverse image, or if you like, the pullback of A along F. And now the essential nature of f to the minus 1 of A, which is a very important concept for thinking about topos theory, the essential nature of this subobject here is really specified by the statement in green here, which is something we've already encountered. And this is this important result, which is sort of an equivalent way to characterize f to the minus 1 of A, is just to say that it's a monomorphism with the property that for any arrow h into x, we have h is in f to the minus 1 of A, if and only if f after h is in A. So this turns out to be an extremely useful kind of result, because when we tie it in with our previous sort of considerations and we think about set to the power of c, it gives us understanding of inverse images, and it gives us a lot of understanding about what the structure of the subobject classifier is and how it actually works. So we'll now think about set to the power of c, and we can use the inclusion lemma 3. So, I mean, again, when we have this inverse image, f to the minus 1 of A, and also notice I'm calling the object it emanates from f to the minus 1 of capital A, because why not? I don't know what to call it, and this is common convention. But the important thing is this, okay? The important thing about monics is always the arrows, really. Anyway, so we can think of f to the minus 1 of little a as an inclusion monic, if we like. I mean, why not? The theory of pullbacks only really tells us what this thing is up to equivalence anyway, so we can pick any of these kind of equivalent sub-objects to think of it as. But in most practical cases in set to the power of c, why not think of things as inclusion monics? Then they're literally sort of including structure inside other structures. In other words, we can think of this f to the minus 1 of capital A as really just having sort of components which are just like subsets of the, like E-type figures of X and so on. So, okay, we'll think about set to the power of C. And if we want to think of f to the minus 1 of A as an inclusion monic, then of course each of its components as a natural transformation is just going to be an inclusion function. And then the important thing is, what's the structure of the kind of E-type figures of f to the minus 1 of capital A? And in this case, we can use our inclusion lemma 3 to tell us that the E-type figures of f to the minus 1 of capital A basically consist of the set of phi in x of E, which are going to be such that phi under arrow is in f to the minus 1 of A. Okay, that's sort of just a direct application of this inclusion lemma 3. But then we already know that phi under arrow is going to be in f to the minus 1 of A if and only if f after phi under arrow is in A. We have this from this green result here. Okay, so we can rewrite this like this, and then we can apply our natural lemma to rewrite this as the set of phi in x of E, which is such that f subscript E of phi or under arrowed is in A. And then, we could, and also the S action is basically just the, and so that really defines, since this works for any E, that really defines the structure of f to the minus 1 of A, except we want to know how the actions work. But since we're representing f to the minus 1 of A as basically like a load of subsets of X, we just have the S actions on f to the minus 1 of capital A just look like restrictions of S actions on X as usual. Okay, so that's what I'm saying here. But, we can even go further because what is the sort of subobject A that we started talking about? I mean, I've been saying that it's a good idea to think of these sort of monics as inclusion monics when we can. And so what about if A itself is an inclusion monic? Well, then things get even simpler and more familiar, because in this case, inclusion lemma 3 basically tells us that we can rewrite this purple expression here as just the set of phi in x of capital E, such that f of E of phi is in A of E. Okay, because basically inclusion lemma 3 tells us that when little a is an inclusion monic, then we're going to have that capital A of E. We can just think of that as a set of theta in y of capital E, such that theta arrow is in A. And if this is the case, then this purple set here is going to be equal to this orange set here. And this is a nice kind of way to think of the inverse image, because it basically is telling us that the way that this kind of inverse image monic can be computed, if we're thinking of it as an inclusion monic, and if A is an inclusion monic, is basically just to say, well, the kind of the kind of E-type figures is basically just to say that, well, the kind of E-type figures of f to the minus 1 of capital A is just going to be the set of E-type figures of x, which is such that if we do f on them, we get the kind of E-type figures which belong to this substructure A of y. So basically, in this kind of viewpoint, computing inverse images just looks like a kind of direct high dimensional kind of analog of the way that we compute inverse images in the category of sets. So anyway, now we have this understanding of inverse images, we can really start to understand more about the structure of the subobject classifier. In particular, we can understand how S actions work upon it. So let's just remember how it was that we sort of found the E-type figures of our subobject classifier. So we have these correspondence here that theta is in omega of E, corresponds with an arrow theta under arrow from hom E comma blank to omega, which corresponds to this subobject theta under arrow star of hom E comma blank. And now let's think about what happens when we have an arrow S from E to V in our category C. So we're really interested in like doing this S action on this theta in omega of E. And so we really want to know what is this omega of S of theta. And that's going to be in omega of V. And so when we apply our Yoneda correspondence, of course, this omega of S of theta becomes omega of S of theta under arrow. But now we can use our action lemma to rewrite this as theta after h to the power of s. Remember this h to the power of s, this natural transformation between Hom functors that we can compose with to emulate the effect of doing actions. Well, we can use that now to rewrite this as theta after h to the power of s. So we can use that now and rewrite this expression on the right as theta under arrow after h to the power of s. And again, just let me remind you, using this s upstairs is just a kind of convention. This is nothing directly to do with exponential objects or anything. Anyway, once we've got this, what we can then do is just use our kind of correspondence associated with the presence of a subobject classifier. So we can say, well, this is just an arrow into omega. So using the property of the subobject classifier, we can just convert this into a particular subobject of hom v comma blank, and in particular that's going to be theta under arrow after hs star, okay, the subobject classified by theta under arrow after h of s. And it turns out that this is equal to the pullback of theta under arrow star along hs, okay, and we can see that here. So this is the basic story, and this is important because we can really think of this subobject here as the result of doing the S action on this subobject here. So the way we get this result here, in particular this equality, is to invoke the pullback lemma. So the pullback lemma basically says that if we know that this big rectangle here is a pullback square, so the pullback lemma basically tells us that if we know that this right square is a pullback square, then this big rectangle is going to be a pullback square if and only if this left square is a pullback square. So we're going to then have that this blue arrow here is the subobject classified by theta under arrow after hs if and only if it's the pullback of theta under arrow star along hs, which is what we call hs to the minus 1 of theta under arrow star. So how do we use this idea? Well, the basic idea is that we know we have the kind of, think about this kind of set of E-type elements of omega. Well, okay, if we're being really technical, we really just know that these are in correspondence with these kind of sub-objects of hom e comma blank. But, you know, we don't really know what to call the elements in this set omega of e. So why don't we literally think of them as these kind of sub-objects of hom e comma blank, because they're the kind of things we can compute. I mean, it's worth bearing in mind that these things are really just in correspondence with each other. And so in certain cases, you want to remember that and apply the isomorphisms and probably come up with some independent names for these things as elements of omega of e. But really for us, why don't we just think of the elements of omega of e literally as inclusion monics? Okay, this is the kind of thing we were drawing in our pictures up here. We just sort of think about the different inclusion monics into these hom functors, and we think of these as the E-type figures of omega. So we think of omega of e as the set of inclusion monics. And so a particular one, let's just call it psi IE, where I is just like some index. It's just like labeling which one it is. And this is just an inclusion monic into hom e comma blank. And so suppose we have such a thing, we have such a inclusion monic, and we're really thinking of it as a member of omega of e. And then we really want to understand what's the nature of this kind of function, omega of s, which is going to be a function from omega of e to omega of v. Okay, we want to understand how this kind of s action works under our subobject classifier. And so according to the argument I've just kind of given, we can essentially, if we want to represent everything in terms of inclusion monics into hom functors, then we can essentially think that the result of doing omega of s on this E-type element of omega, psi ei, is just going to be the pullback of psi ei along hs. Okay, And that's it, because it's this kind of formula here, which really allows us to understand how the S actions work on things in our subobject classifier. And this allows us to be able to actually compute, the full form of what the subobject classifier looks like in a given category set to the power of C.